approaching, and they have a console available. This is what you can see now. You have 16 push buttons on it in order for the crew to possibly change the movements of the ATV. The two white buttons are commands to stop the ATV where it is and to go back to a given point. The orange push button ejects it into a parking orbit, and in an extreme position you have the red button, which also makes it possible to put the ATV on the parking orbit.
Well, only used if absolutely necessary, I would imagine.
Yes, of course, when nothing else works.
So that does go to show that the crew members have something to do. There's the control panel, and there's a display of what's happening. In other words, through the optical control board, it's possible to see the arrival of the ATV. So here we are. Let's imagine we're here. I'm in the Sveda module. There's a camera. This was actually placed outside the module by Sergei Krikalev, an extravehicular sortie. So the camera can see the ATV. It could have been looking here at this point at the rod, the docking point, but actually it is targeted up here. There's a cross-shaped target up here that it's looking at, and that's what it's going to be focusing on.
Yes, quite. When the rendezvous target is properly aligned, it means that the mechanics there are okay and that it fits together.
You've been involved in the programs, the simulations, and thanks to this, you've brought with you a couple of things to show us. These are things that are used if there's a slight hitch where the crew members have to intervene.
Yes, either for safety purposes or else to save the mission. First example now. Here at the center, you see a small target. It's the rendezvous target. You see the docking mechanism underneath, and this is one of the scenarios we have in our simulator. You see the small circle, the target in the upper part, which starts drifting away. And as long as the small circle remains within the big circle, the situation remains acceptable.
So this is the cone that has to be fitted into 4 degrees.
Yes, it's the closing corridor, 4 degrees. And whenever it gets out of the white circle, the crew presses the escape button so that the ATV regresses and they wait for a couple of days.
That was a simulation, and we saw what happens if the human beings have to intervene. Now let's take another example. Everything's going fine, the systems worked correctly, but, Manuel, let's take a look at this.
Okay, now the distance is 2 meters, centering alignments are okay. The crew checks that the cross remains inside the circle. The distance is now 1 meter. From then on, no command is possible any longer by the crew. They can't change anything to the situation anymore. They're unable to correct anything, and they're sure that the alignment is correct. So the cross gets back to the center because the rod gets into the center of the cone, and you'll see the word capture displayed on the right-hand side. It's been captured, and it should also be displayed on the other side, on the left-hand side. Now, what happened this time is that the ATV hasn't recognized that it's been captured. And so that it's up to the crew to tell ATV that it's been captured.
This is reassuring, after all, for you as an astronaut, isn't it? It goes to show that the crew members have a vital role to play. And have the last word.
Yes, quite. They save the situation.
The crew also have other tools and aids available. And there's one that you helped to develop. It's absolutely amazing. It's very simple. This is a perfect example of what Clairvoy can produce.
Well, as you can imagine, it's not haphazardly that the crew presses one button or another. So I prepared a malfunction matrix, as we call it. Here you can see it. You have a number of parameters here on the left-hand side, parameters to be monitored. They're all on the screen, on the video screen. And here on the right-hand side, you have explanations for the crew telling them what to do under such and such circumstance. Here, for instance, it's if you deviate by 4 degrees, press the escape button. And the closer you get, the redder it becomes, and the more complicated the situation gets. And what the crew does is turn the panel round and monitors, follows what the action has triggered. And in case of another problem, they have another solution available. So it's a manual panel, which is very simple, but their job isn't that simple at all.
That really is quite impressive. It's very simple, but it's sophisticated as well. How long did it take you to produce?
Tens of meetings in order to come to an agreement as to the content of it and to the number of parameters that are to be monitored, because it is impossible to monitor too many.
Which means, and this will bring us to a second system, which means that there is the training of the crew that's obviously very lightweight at that point.
Well, the vehicle is an automated vehicle and it's self-monitored, so that 2 weeks are sufficient for the crew to be trained in Cologne at the astronaut center. So the crews have trained at Cologne and they love that job because 2 weeks suffice for that.
How long does it take to pilot Soyuz?
Several months. Because it's much more complicated.
Here we have another example of a sort of aid for the tool. This makes it possible for the crew members to calculate distances or assess distances. Here you can see the target that's aimed at, and the closer you get, the bigger it is, and the smaller it is, the further away you are. This is what you can see. But to help you understand the distance, and Jean-François will help me here, they place this sort of ruler or slide rule onto it, and you can see that here the ATV is 7 meters away from the Russian module, and in this particular case, the rule is on the video screen, and if it's at this size, this dimension, then the docking has been carried out. And it says CHOP. What does CHOP mean?
At a distance of 1 meter, the crew must remain hands-off. It's a rather simple system. We want the crew to be totally independent from the information they receive from the ATV. They monitor everything from a camera, which is on the station, and a very simple ranging system is being used, which is very secure.
This really is tremendous. The ATV is 3-in-1. It's a highly sophisticated device. It's a spacecraft, the most complex that we have. It's an autonomous vehicle as well. It's capable of moving around space. And it's a module for the space station, because it's going to be docked up there for about 6 months. So it's a 3-in-1. Now, if I had to present this to a TV channel boss and say, look, this is a tremendous premiere in Europe, we should do something about this, and then the editor would say, well, hang on, this progress has been around for a long time now and it works. So where is the extra performance?
Well, it's true that we could have used existing rendezvous and docking systems that our partners already have, but we've decided here in Europe to develop a special reconnaissance and rendezvous and docking system with a high degree of accuracy, 10 times more than is necessary actually, so that the ATV needs no cooperation from the ISS to have a successful docking. So it's a visionary system actually, because it paves the way for the future.
What about this technology? What is it going to be used for? I mean, it's a boost for European industry, which is wonderful. And, well, as Michel